Well, thank you. So we've come to the end of the week, and we'll be talking about not quite what we're all doing right now, but what's to come in a few years. And in particular, I'll be talking about the James Webb Space Telescope to begin with, and then we'll look ahead to the AFTA, WFIRST, and other spacecraft to come. And of course, I have to begin this by saying this obviously is not a talk solely on my work. It's a talk on the work of approximately 5,000 people, whose names I have not listed here. So with the James Webb Space Telescope, of course, we're going to be doing all sorts of science from solar system to the high redshift universe, which is what it was really built to address. But thinking in terms of exoplanetary science, right, the kinds of questions that we'll be able to address with James Webb really span the whole range. You know, looking at understanding the properties of giant planets, Webb will be fantastic at characterizing these systems through imaging and through transits to look at their compositions, their atmospheres, properties, and start to discriminating between the different possible planet formation mechanisms. Of course, James Webb will also be able to study circumstellar disks, image debris and protoplanetary systems. And we'll also be able to start pushing into new regimes looking at lower mass planets for direct imaging below 1 Jupiter mass and tracing the properties of these. And so there's a lot of things to think about. And this particularly for the young audience in the room, right? James Webb is going to be a major part of your career. This will be launching in about 4 years, and we expect to have hopefully at least a 10-year lifespan of the observatory. This is going to be a fantastic resource. It's going to change the landscape, just like ALMA is changing the landscape now. And so this is a real chance for you to start thinking about what do I want to do? How will I make use of this facility? So what I'm going to say in this talk, I'm going to start with the first half is really going to be about what is the James Webb Space Telescope? Why is it this big ungainly thing you've seen pictures of for a bunch of years? Why is it being built the way it is? And where's the project right now? And then in the second half of the talk, I'll move into specifically the exoplanet science that we hope to do, looking at what properties of the telescope affect how well we'll be able to do coronagraphy and what the capabilities of James Webb are. So what is the James Webb Space Telescope, right? So to put it in context, there's this figure here which shows James Webb compared with Spitzer and Hubble. And you've seen this picture before, I'm sure many of you, but stop and look at this, right? So one James Webb Space Telescope segment, one segment is 3 times the collecting area of Spitzer, right? Just let that sit in for a second. This thing is huge. This is, 3 segments is Hubble. So in terms of the area, the collecting area, it's about 6 times the aperture of Hubble. And what I've always found, my favorite fact about this space telescope, 6 times bigger than Hubble in half the mass. It is an astoundingly lightweight observatory. For scale, I'm pretty sure, someone told me that Sphere weighs the same as all of JWST. So this is it's an engineering marvel to get this lightweight. And then to fold it up, when it's folded up in its stowed configuration, it's actually only 75% the size of Hubble. And that's what lets you fit it into the Ariane 5 and put it up to the Lagrange point L2 where it will be operating. In terms of why it's designed the way it is, there's actually been a real change in telescopes in the last 30 years on the ground. So on the right or left here, I'm showing this is the Mount Wilson 100-inch, just up the hill from us here. And this is a telescope that's almost 100 years old. And it's 100 inches across, of course, and it's a very long, it's a Ritchie-Chrétien classical design, with this long truss that holds the mirror down here passively in place. And this is another very similar old-school classical design telescope, very passive, in some ways not very technologically advanced. You know what telescope this is? Anyone want to guess? This is Hubble. Right? Hubble is an old-school classical design. It's Mount Wilson 100-inch launched into space in a lot of ways. The modern telescopes that have been built in the last few years really have revolutionized the way we do telescope optics by moving from these big, thick, passive optics to lightweight, thin optics, about 10 times lighter per unit area, which they actually have to be actively and adaptively supported to maintain their shape, much faster optics in the sense of the focal ratio. So if you look at how long and narrow this is versus how relatively short and stubby, this is Gemini, this is Keck, this is a segment for TMT that's being fabricated now. And so this, the revolution in segmented telescopes, in active telescopes, it's what enabled building telescopes on the ground that are now at the 8 and 10 meter class and looking ahead to the 30 meter class. And the challenge now is taking and advancing this technology into space. Sort of as a timeline to visually guide that. This is sort of a California-centric list of big telescopes that were noteworthy. And this is a space list, right? And you look at Hubble is the Mount Wilson 100-inch in space. Well, Kepler is the Palomar 48-inch Schmidt in space. It's the same size as a Schmidt telescope, but in a way better site, right? JWST, we're at the point of thinking about putting Keck 1990 in space, active segmented mirror that we're going to phase up to get the large collecting area at an inexpensive cost, relatively inexpensive, but not yet doing adaptive optics. And the adaptive optics is going to come next. We're going to hear about that later today from Bruce. And of course, I think a lot of us are very interested in the question of how do we take GPI, how do we take Sphere, how do we take MAG-AO, and put those in space on an 8 to 10 meter class telescope sometime in the 2030s. So JWST, this is what it looks like. Of course, we've all seen this. So the telescope is sitting on the cold side of this giant sun shield that's designed to keep this passively cooled, like Spitzer. So this side is warm in sunlight. This side, the whole thing, cools down to about 40 Kelvin, which is going to give it fantastic infrared sensitivity. The optical design, you can see the primary mirror focuses light down to a secondary, comes down here. There's a tertiary mirror, a fast steering tip-tilt mirror, and then the instrument module on the back. It's beryllium optics, just like Spitzer, very lightweight, very good thermal properties at cold temperatures, low coefficient of thermal expansion at cryogenic. And the instruments on the back of JWST in the module behind the primary mirror, there's 4 instruments. It's a consortium, US, Europe, Canada, that have put these together. NIRCam MIRI, and then the guider and the instrument called NIRISS are both Canadian contributions. And they all have a tremendous range of capabilities, far more than I can go into in this talk. But if you look at high contrast imaging capabilities, actually all of them have something to do in exoplanet science. Coronagraphs on NIRCam and MIRI. NIRISS has a aperture masking mode, and NIRSpec and MIRI both have integral field spectrographs. There's transit modes on all 4 of these instruments. It's an incredibly rich complement of tools to support all the things that we can think of now. And Hubble, we're doing things now that nobody expected to do when it launched. So I really hope that there are things that people will do with the Webb that we're not even envisioning yet. Where we are in the process, right? This is a long time in coming. This is a master flow chart of what's going to happen for the next 4 years that I've adapted from Eric Smith. So here we are, tail end of July in 2014. What's going on right now, right? The spacecraft is being built. The sun shield is being built. All the science instruments have been built and are at Goddard Space Flight Center in Maryland right now, undergoing the second cryo test campaign. They're all cold at 40 Kelvin or below right now, and being put through their paces, doing all sorts of instrument checkouts and testing, software testing, everything. And then there's another campaign to come a year from now. Meanwhile, the telescope, the mirrors have all been fabricated long ago and completed. The backplane frame of the telescope is coming together now, and this will all flow together. Next year we build the telescope. The telescope and instruments are merged together and get tested at Johnson, and then they flow down. And the thing to keep in mind in the schedule here, actually, is it's pretty packed. There's stuff to be done, but these numbers in red are all the schedule contingency that we still have. And so people say, is it really going to launch 2018? Well, you do the math. Right now we've got 13 months of slack. So there's still room. The schedule is designed assuming there will be surprises, and we'll still be able to hit the launch date, and people are working very hard towards that. Yes?
What if you actually don't hit anything? Can the launch actually happen before that?
It is possible to move things up earlier. There are launch windows throughout the year to get to the L2 location. I suspect that there will be surprises, and if you end up actually having spare time, you're just going to use it for additional testing and additional practicing and dry run of commissioning. So I don't think we'll launch early, but I think that there's a good case we won't launch too late. More fun than showing all these diagrams, we can actually show pictures of a tremendous amount of hardware right now. Right? So here are all 4 of the flight instruments. NIRCam, there's actually 2 of it. There's 2 mirror image copies of this instrument were built to provide redundancy, and because it's the primary wavefront sensor, it's the main instrument on the telescope in a lot of ways. But also just if you have both of them, it doubles the field of view. So this is a 10 Hawaii 2RG mosaic imager, going to cover huge parts of the sky. Near-infrared spectrograph, the biggest, probably most complicated of the instruments. MIRI that goes out to 30 microns. And here again, the Canadian instrument has the guider on one side and a slitless spectrograph on the other side. And so all of those instruments are now, as I said, mounted together in the instrument module. So here they are. This whole structure. This is carbon fiber frame that holds them together, and they've been put together and assembled and aligned exquisitely precisely over the last year or so. And then this whole thing picked up and put into, this is the Space Environment Simulator chamber at Goddard, where you cool the whole module down to operational temperatures. There's a telescope simulator there that's feeding in beams to put all the instruments through their paces, and this is all working more or less quite well. There's a couple occasional surprises. I think one of the more notable ones, the emergency exit sign caught on fire in the control room. I mean, little silly things like that. But the good story is the actual flight hardware is working really well. And this testing is going on right now. It's 3 shifts, 24/7, started in June, going till September. So it's a very serious test campaign, getting a lot of data to prove that things are where they need to be. And then we'll be doing some change-outs and upgrades later this fall, fix what we need to fix, and then get ready for the third set of tests all next summer. The mirrors. So here's some of the mirrors for actually all of the mirrors for JWST. This is what primary mirror segments look like, 1.4 meters on a side. Secondary mirror, tertiary mirror. This is the fast tip-tilt steering mirror. And this is all the mirrors, all 18 primary mirror segments bundled up in their individual storage pods, basically just little nitrogen perv valves keeping them nice and clean while they're sitting at Goddard right now waiting for the telescope to be built, which will start in about a year. And that's, so here's the back plane. This is the primary mirror back plane center section. There's 2 wings that fold out that go on either side. You can see this is a really big precision carbon fiber structure that's actually now been complete and has just arrived last week at Goddard. So it's now there, ready for the testing. So here's the Pathfinder Center practice section of that. And so this is one of the first secondary tower deployment tests. So you can see that the secondary is held up on these long carbon fiber struts. There's hinges here and at the base, and it all folds up. You've probably seen the videos of that. And the ground test process just runs through all these things, just tests the mechanisms, gains a lot of confidence that the deployments will go according to plan. Here's a shot very recently doing some test assembly of one of the segments. This is not a flight segment. This is an engineering unit, the practice segment, basically. And this is being assembled in this giant robot arm crane. It's an amazing facility at Goddard. And so all the segments, this year we build a practice unit with 3 of the segments that will go and do some more of the test integration flow with that. Next year we build the entire primary with all 18 segments. The spacecraft is coming together. This is actually just cross town at a Northrop Grumman facility near Los Angeles. This is the engineering unit. Build a whole model of the spacecraft, the computers, the bus, the attitude control, the star trackers, and then you build a second copy that's the flight instance with incorporating lessons learned. So that's all moving ahead on schedule. Here's the sun shield. This is the first test of a full-size membrane. This happened about a year ago. So you can see this is just a huge tennis court-sized device held taut by there are these cables at the edges that pull it and tension it in orbit. The point of the sun shield, right, this is just a 5-layer insulator that each layer blocks about 99% of the light, and so you end up blocking about 99 to the 5th of the light. So that's how you get the telescope to be so cold on the backside when it's in full sunlight on the front side. It's very exciting to be able to show. This photo is just a week and a half ago, the first 5-layer deployment test that happened at Northrop. I wish I had the video. The video hasn't been approved for public release yet, but it is great to see this thing coming out and deploying. And right now it's at the stage, this was done, it's not yet mechanized, so this was all people turning cranks and pulling on cords. But they'll do it again in September with more automation, do it again shortly after that and with more automation, and just keep iterating down the road. And this is, as I said, this is the engineering one. This is not the flight unit. But they're making lessons learned. They found there was one place down here where a cable snagged, and so they can rework exactly how that piece of metal is shaped. And it's a good engineering flow, and we're actually on schedule, right? People have been for a long time saying, "Oh, JWST, it's going to be horribly late." As more and more of the pieces come together, it's easier to say the project has been executing on track for the last several years. Now, I'm not going to say that there aren't risks and surprises. As we go down the next steps of processing, we'll see what happens, and we'll adapt. But I think we're on track. And the real big showtime comes in about 2.5 years at NASA Johnson. So this is the Chamber A test facility in Houston. It's the world's biggest cryo-vacuum chamber. Inside, it's 40 meters tall. It's 20 meters across. The door is 15 meters wide. So you can put your house in there, pump it down to vacuum, and take it down to 11 Kelvin. And so people ask the question, are you going to actually deploy all of JWST? Are you going to test it on the ground? This is where you test that whole facility. Now, it's not going to do the full deployment system sequence in there because the telescope's designed to operate and unfold in 0G. So if you want to test the deployments, you have to do it with bungee cords and ropes to offload the weight of the structure in 1G. So you do that out in this large clean room. You do that in other facilities like at Goddard. And then you take and put the deployed telescope in here. It'll be facing up, and there's telescope simulators, and there's interferometers, and we'll check out all the optical performance and be confident that we can align this telescope before we put it up there. Just another bit of fun history of this. We were all out looking at the shuttle the other day. Why does NASA have this gigantic vacuum chamber, right? Was it built for JWST? No, it was built for Apollo, actually. So this is about 50 years ago, one of the Apollo capsules in there. And they would actually put live astronauts in spacesuits inside these spacecraft. And if you're going to go to the moon, you want to be sure that your spacecraft will work, so test it in a vacuum chamber. And so this whole facility has been revamped for JWST. They didn't need to, for Apollo, take it down to 11 Kelvin. So they built a huge helium shroud inside. Really, it's an amazing accomplishment that's all now totally done, totally ready to go. As I said, we'll be taking the first, the practice engineering unit with 3 segments. And so starting in January of next year, we'll have that 3-segment unit in here to test the facility, test the interferometers, and be sure that when in 2016 the telescope gets there, we'll be all ready to go and run through that process. And so here we have sort of the rundown of the next 5 years. The manufacturing of the spacecraft and the instruments is going on this year. Those pieces all come together next year, such that by the end of sort of middle of 2016, we will have the fully assembled telescope, the fully assembled instrument module. Basically, the entire top half of JWST will be assembled, and we take that and bring it to that test chamber and go through 2017, mid-16 into 17 to do that test. And then it actually all comes out here to Los Angeles. And Los Angeles at Northrop, right by LAX, just south of the airport, is where the telescope and the sun shield will be mated together and then that whole system goes down to French Guiana. It launches on an Ariane 5 rocket from South America towards the end of 2018. So let me pause here and ask, are there any questions about JWST as a whole or any of the hardware I just showed or anything like that? Okay, so then I will move on to the question of how. The right thing I wanted to say before I move on, before we launch, a year and a half before science really starts in mid-18 is when the Cycle 1 proposals are due. So it's not that JWST is 5 years away. It's that you have 3 years and a bit to write your proposals, right? So start thinking about what you want to do with JWST and what you're going to put in this highly competitive but very exciting proposal opportunity then. Yes, so I don't know about workshops specifically, but a lot of it will look very familiar to anyone who's used Hubble. We're reusing the software and the proposal. The question was, what does the proposal process look like? Will there be workshops to train people? And a lot of it, we're reusing the parts of the Hubble flow that make sense. You can actually go in right now with the Astronomer's Proposal tool for Hubble and create a new JWST proposal and play with it. We're having at the AAS meetings, you stop by the Space Telescope booth and you can play with some of the software, look at the NIRSpec planning tool and things like that. We're actually looking for feedback from the community on what you need to help plan your observations so we can make sure the tools are there. Right now, in the next 2 years is the time to build all the tools the community will use 3 years from now. So if there's something you want, think about it and make sure people at the Institute know about that. So, coronagraphy with JWST, right? This is a telescope that was built first and foremost to do extragalactic high redshift universe science. Planets weren't even on the drawing board for direct imaging in some sense when this thing was being planned initially. So how well will it work? So the first thing to keep in mind is that JWST is going to be extraordinarily sensitive. So this is just a plot of the flux density that you can see at 10 sigma detection in 10 kiloseconds versus wavelength. And Webb is this red series of curves here. And so if you look at optical, it's about the same as Hubble. And it may actually be a little bit lower than that with the latest models. But if you look at 2 microns now, Webb is about 100 times more sensitive than a ground-based 8-meter. I mean, that's a fantastic thing, right? This is when you ask, how is it that a 6-meter telescope is 100 times more sensitive than an 8-meter on the ground, right? Well, is there some sleight of hand going on? And the trick is that the background is so much lower in the space. You're not looking through the atmosphere going all those OH lines. And so this is why actually Hubble, Hubble is 10 times more sensitive than Gemini in the optical, just because it's not looking through the atmosphere. And so that's what gives you at short wavelengths this amazing advantage. And then Spitzer, down at 8, 10 microns, Webb is going to be about 50 times more sensitive than Spitzer. They're both cryogenic telescopes in space. So here, this advantage is purely from the fact that it's a 50 times bigger telescope than Spitzer. So it's going to do, you can go really deep with this thing. It's designed to do deep fields and see really faint stuff. It's a little more constrained than Hubble in where you can point it, because you have to keep the telescope in the dark behind the sun shield all the time. The sun's here. You can point basically and sort of keep the telescope between 85 and 135 degrees pointed away from the sun. So it gives you this big annular field around the sky. There's continuous viewing zones at the pole, but most of the sky, you'll get 2 parts of the year that sort of this field rotates and swings through that part of the sky. And the scheduling software will all take this into account for you, but it does mean that you're more constrained in how you can roll the telescope than Hubble. Hubble, there's plus or minus 30 degrees freedom. Webb is only going to have plus or minus 5 degrees. So that's really a challenge for, we're all used to doing angular differential imaging at a single time rolling the telescope. At any one moment, you can only do plus or minus 5 with Webb. But if you want to come back at a different time of the year, you may be able to get a larger range of that. At the pole, you can get the full 360 degrees, just hitting it at different times. Near the equator, you basically have plus or minus 180 degrees in the two passes. And it all just has to do with keeping the spacecraft in the shade all the time. And we'll learn what works well in terms of scheduling and how many rolls and things like that. We'll just have to try it out in practice. The telescope, of course, is going to have active wavefront sensing. And the first thing we do after launch is commission the telescope, and I'm part of the group that's developing and testing and validating the plans for that. The initial deployments on orbit are to millimeter tolerances, and over about a 3-month period after the launch of the telescope, we march down to tens of nanometers positional alignment for the individual segments. And then once you get there, we'll actually have to maintain the telescope's alignment over time as it gets perturbed by the environment. And the 2 main sources of perturbation, one is thermal perturbations. You can imagine as you change the orientation of the telescope with respect to the sun, you change the equilibrium temperature of the sun shield. And so as that temperature change gradually comes in to the telescope, it'll move up and down a little bit. You'll have a little bit of coefficient of thermal expansion type changes in the structure. And so this leads to small variations in the wavefront that will correct on longer time scales. And on short time scales, you have things like vibration from the cryocooler, from the reaction wheels that'll give some figure of vibration. So the baseline plan going in is that we'll be sensing every 2 days, but we'll expect to adapt this on orbit as we learn what the behavior of the observatory really is. And there's a good chance that we'll actually be quite stable, quite sensitive. And that's something that we're actually working on. How do you maximize the stability of this observatory? What are the strategies that you can use? And so this complicated plot here is a simulated schedule of the observatory for a year. So this is just plotting the pitch angle with respect to the sun versus time as you go to every different observation that in this particular realization of a mock schedule. And if you low-pass filter that, because you expect, from detailed finite element modeling, a slow time constant to change the observatory state, you get this red line, slow-pass filtered. And that leads to, and I'm sorry this plot is a little harder to see, but these are simulations of what the wavefront error versus time could look like. And so you have sort of, it jiggles back and forth. This is not adaptive optics where weather happens and you adapt to it, right? This is the thermal perturbations coming in and changing the telescope state, and occasionally you get these big swings that you then have to adapt to. And so you can either think about building schedules that try to minimize the thermal slews of the observatory, or taking your particularly most sensitive observations, your transits, your coronagraphy, and saying don't put those after you've just slewed halfway across the sky. You can also say, well, if we know what the behavior of the observatory is going to be in response to the perturbations from attitude, then we can actually do predictive wavefront control. We can take some of the sophistication in control algorithms developed for adaptive optics and apply it to the case of a space telescope. And I think that's broadly a really important theme to keep in mind. The ground is where all these cool new algorithms and advanced controllers and predictive controllers and things like that are being developed. And then you need to say, how do we take and adapt this and use the same technology in space to maximize the performance there? So how stable is this telescope going to be in the end, right? The requirement for JWST is that it has to be, the telescope wavefront has to be more stable than about 50 nanometers over 2 weeks, a 2-week period, for the biggest possible change in orientation with respect to the sun before you do any control. So, okay, 50 nanometers is actually a lot of wavefront area variation, but this is before you've done all the things I was just talking about. We haven't done really detailed simulations yet for the specific case of realistic scenarios. All the simulations are on the worst case scenarios like this to validate the requirements. But using some simplified simulations that aren't the full detailed multi-million element finite element modeling, it doesn't seem unreasonable to say that we're going to have on longer time scales, we'll keep the variations less than perhaps 10 or 20 nanometers using the types of control strategies I was just talking about. On short time scales, 10, 12 hours, we'll be looking at the vibration terms coming in at something like a couple of nanometers. And in fact, for back-to-back observations, science target PSF star, it's plausible to expect sub-nanometer stability. That's because this telescope is designed to be so cold, right? The cold side is very well insulated from the sun-facing side. And so you do a change, and an hour later, as you look at your PSF star, if you've moved the telescope only by 5 degrees, it can be extraordinarily small variation. So we should have really good ability to do PSF star subtraction the same way that we've been doing with Hubble. This all remains to be proven. There's a lot of caveats here, but we should be thinking about both what the nominal performance is as well as what the sort of 95% confidence performance will be. So what are the science cases that we can do with the James Webb Space Telescope, right, specifically for exoplanet imaging? What are the tools we have? So NIRCam, right? The NIRCam instrument, which is from about 0.6 microns out to 5 microns, has 5 different coronagraphs in it. There are 3 coronagraphs that are spot occulters. These are band-limited Lyot type coronagraphs. And then there are 2 wedge occulters, familiar from the exercise we did with STS, right? You can put the star at a different place along it to select what the width that's blocked is. But it's optimized for there's a nominal wavelength dependent location. And so these are not, compared to what we're doing on the ground, very aggressive coronagraphs. They're fairly classical band-limited Lyos. The Lyot masks were designed. These shapes come out of doing optical simulations, assuming pretty large pupil shear. So that it was designed before we had, we knew how well the pupils would be aligned. So it's designed to be very tolerant to whatever the misalignments on orbit are. The spot occulters, of course, give you 360-degree coverage around the star. And so if you're looking at disks, this is going to be a good choice. If you're looking at surveys for new planets, this can be a good choice. The wedge occulters provide slightly better suppression at close-in inner working angles, and that will be good for cases where you know ahead of time where a planet is and you're trying to do deep characterization of those. And these instruments are written up in a number of papers by John Christ and by Chaz that you can go and consult for more details. MIRI, this is the mid-infrared instrument that operates at from 5 to almost 30 microns. It has 4-quadrant phase mask coronagraphs as its primary type of chronograph. There's 3 of these quadrant phase masks there. This is, in some senses, related to the vector vortex that you saw yesterday. This is, is a square, a checkerboard of phases, whereas the vector vortex is a full sort of generalized circle with continuous variations. And the benefit of these phase masks is they let you work into 1 lambda over d, better inner working angle. So why is that important for MIRI? Right, MIRI is at longer wavelengths, so the diffractional emitted PSF has scaled up quite a lot. And so you really want to work at 1 lambda over d if you can, because that will get you into smaller inner working angles. Still fairly large compared to what we're thinking about for Hubble. There's 3 of these. Each one is optimized for a single wavelength at 10, 11, and 15 microns. And the 10 and 11 pair is designed to go after this ammonia feature, where the 10.6 is on the feature, and then the 11 provides a continuum adjacent to that. 15 gives you both the overall black body slope, and you can look at some of the silicate features, and then there's another filter out here at 23 microns, which is not a 4-quadrant phase mask. That actually is just a classical Lyot coronagraph, big circle mounted on this supporting bar. Again, so 23 microns, right? This is very long wavelength. The PSF, even with a 6-meter telescope, is quite large. So this spot there, the inner working angle is over 2 arc seconds, right? So a lot of the disks that we're used to seeing now are going to be entirely hidden behind that. But for nearby bright disks, right? This is designed to go after the Fomalhauts and the Eps-Aries and the Vegas of the world at extraordinary sensitivity. You can also use this with any of the filters in MIRI, but you're not going to have an optimized Lyot stop. It's not going to be really blocking much of the diffraction, but it will prevent you from getting saturation. And so if you want to look at possibly 5 microns, 7 microns, some other wavelength, MIRI has filters spanning this whole range. There's a question of how well we can do PSF subtraction using this in cases where it's not optimized, but you can at least get data at that wavelength. So that's an open area that I think people will explore. There are some people interested in that. So what's the performance look like compared to ground-based systems? So here's just a contrast plot showing 5 sigma predicted contrasts versus separation. And I should put the caveat here that these plots are generated assuming a relatively conservative estimate of 10 nanometers RMS wavefront error variation between the science target and the PSF star. And as I've been saying, that we may be able to do better than that in single epoch visits. And this is also not yet using any of the advanced PSF subtraction techniques such as Loki and CLIP, right? With Hubble, we're now beginning to reach, using those techniques down to the fundamental photon noise limit. I think with applying those same techniques to JWST, there's a good case to be made that if we can reach photon noise subtractions, these will come down by a factor of several, perhaps a factor of 10. And this really remains to be proven, and I think this is something that all of you that are thinking about PSF subtraction techniques will have a chance to try out on this telescope and really learn what kind of principal components, what kind of methods will push this to its ultimate limits. But this is limits we're confident in saying right now. Just keep those caveats in mind in the next several slides. So this gray dashed line is some of our first light data from GPI, and so you see at small separations, right, the ground-based AO systems have an advantage. They have better, more optimized coronagraphs and diffraction suppression systems, and so they'll be able to dig a bit deeper by maybe a factor of 5 or 10 at the smallest separations. But then at wide separations, Webb will do phenomenally and do a lot better. GPI actually, this is the edge of our field of view at about 1.4 arcseconds. Sphere can go wider because they have a bigger detector in their IRDIS imaging mode. But out here, Webb, if you look at this, is actually down at almost a few times 10 to the minus 9 at 5 arcseconds at 2 microns. And so if you think about, we saw earlier this week, Jared showed some of the work that they're doing it with MAG-AO looking at Alpha Centauri, right, which they're working at wider separations. You can actually get to very interesting low contrasts if you're looking at the very closest stars. So that's one thing that'll be very exciting to do with JWST. But let's go to longer wavelengths. Oh, first let's add some planets here. So this is, of course, the beta PIC and HRD 799 planets, all detectable with these systems. So let's go to longer wavelengths. Let's go out to 3.5 microns. This is L-band on the ground, right? And so Webb actually is picking up more or less consistently with what we're seeing with these two lines are LBT and MAG-AO. And so Webb is digging a bit lower than them at close separations. And then at wider separations, of course, gets much lower. We're not limited by the thermal background, looking through the sky that we see here. And these are model contrasts for a set of planets. This is from a paper by Chaz in 2010, really useful reference of what the planet brightnesses will be in all the different filters for JWST. For a G2 star, around 10 parsecs scaled to here. And so actually, this is a really interesting point right here, that for relatively young stars, actually, under 100 a couple hundred mega years, we'll be able to comfortably push down to less than a single Jupiter mass, to Saturn, maybe even Neptune, super Neptune planets, right? We know that these exist at close separations from RV, but are there HRD 799 type systems with wide Neptunes, wide Saturns that aren't 10 Jupiter masses but are one or a few? And Webb will, I think, do an extraordinary job at pushing down to these intrinsically much fainter objects. It gets even better as you go to longer wavelengths, right? This is where Webb is really going to shine. So here we are, 4.5 microns, like the M band on the ground. And this is a Keck contrast curve from Raphael Galichet's paper on 8799. And you see these planets are actually barely detectable at 5 sigma from the ground. The beta PIC B detection is about 10 sigma. And this really is just being hit by looking through the atmospheric soup. And Webb just instantly digs down at least a factor of 10, factor of 50 below that in contrast due to the better location, right? And so that, as the planets, if you look at the planet curves here, right? As you change in wavelength, go longer, the planets just keep getting brighter. And so this is where there's going to be this tremendous synergy to do the long wavelength characterization of these planets with JWST. How about MIRI?
Is cooling also superior or not?
Is
The cooling of the telescope, does it have an influence?
Oh, the cooling of the telescope is a huge part of it. The entire telescope is at 40 Kelvin. Right. So the lower background, I was sort of conflating the atmospheric emission and the thermal emission from the telescope itself. Yes. 10 to 15 microns, right? There are no planet points on this because obviously no one's imaged a planet yet at 10 or 15 microns from the ground. The background is just far, far too high. But with the coronagraphs on MIRI, the quadrant phase mass coronagraphs, showing here the 10, 11, and 15 micron curves, actually should be able to push into these same territory, and it may be possible to image, for instance, the HR 8709 planets using the MIRI coronagraphs. And so here, this is a plot. Again, I've kept it normalized the same way to the G star at 10 parsecs. And so you see, that some of these are detectable. There's a 1 Jupiter mass planet at a giga-year that you can see. But you have to get out to several arc seconds, quite away from the star, to see that. But if at 10 parsecs, this is 40 or 50 AU, right? This is the same ballpark as we're seeing the HR 8709 planets. This is a place where we know planets exist in this part of parameter space. But what's even more exciting with this is to think about the lower mass stars. If you think about M stars, right? This is a paper by Ruan et al. From a few years ago. But of course, for an M star, you keep the planet brightness the same. You scale the stellar brightness way down. And so MIRI, looking at nearby M stars, which there are many, right, of course, will do a fantastic job at finding planets around these stars. And this is a part of parameter space that the ground-based AO systems will struggle with due to the intrinsic brightness of the stars. These are not good natural guide star wavefront sensing targets. Of course, JWST, you can get these contrasts independent of the brightness of the star that you're looking at. This will be a very exciting part of parameter space to work in. Disks, of course, there'll be lots to do with disks. As I said, some of the chronograph modes are optimized to work at larger separations, like at the MIRI chronograph here, the simulations from Carl Stoppelfeld. So here, this is actual Spitzer data. This is what the ring might look like with JWST at 24 microns, resolving out the inner and outer components of the disk, and with a plausible planet in there that might be something that isn't Fomalhaut B, but perhaps is Fomalhaut C or something in there that might be detectable with JWST using that 15-micron chronograph mode we were just talking about. Here's a simulation from John Criss looking at a debris disk or transitional disk. And of course, you can get really nice simulations, really nice detections at this optical depth, which is close to the true optical depth of the system. You scale down to a disk that's 50 times lower. Remember, we were told earlier in the week, most of the nearby debris disks that we know are there from infrared excess have not yet been imaged. And so JWST should be able to push into the sensitivity to get down and image those. The inner working angle on this depends on the chronograph, but 0.2 to 0.5 arc seconds, depending on the mode. Some work by Jeremy Le Breton showing the simulations of disks at a variety of wavelengths from 2 out to 23 microns. Something to keep in mind with Webb, there's a huge suite of spectral filters in NIRCam, about 20 filters you can use. Going after ices at 3 microns will be very interesting. Silicate features you can look at with those MIRI filters. And another thing just that people haven't really done detailed work on yet for high contrast imaging, but I think will be very promising, the integral field spectrographs on NIRCam and MIRI. Right? These have resolution of several hundred to several thousand. How well can we do PSF subtraction on these is an open question. These are not lenslet-based ones optimized for high contrast imaging. They're slicer designs. But if we can do PSF subtraction using these types of low-key clip algorithms, we should be able to dig down and actually do spectroscopy of these disks, spectroscopy of planets at moderate resolution. And this is work that, for instance, that Quinn has done using OSIRIS at Keck to get the high spectral resolution spectrum of HR 8799. This is something that Webb will be very strong at too, I think. There's an aperture masking mode in NIRISS. I have to go a little fast through these slides just because we're running short on time, but I would invite you to talk in particular with Alex Greenbaum at this meeting, who's been working a lot on this. We've heard a lot about why NRM is so exciting to dig into close separations. Here's the same plot again. This is where the part of parameter space that aperture masking will be strong in. It gets way inside this inner working angle problem of the other chronographs. You can get into very small separations, admittedly not quite at the same contrast. But this will be very strong for following up GPI and sphere detected planets. NIRCam will go after the ones at wider separations. Whoops. And NRM may be able to go after the ones at smaller separations. I should say high contrast imaging is not limited to planets. You can look at AGN, you can look at quasar hosts, and you can actually do imaging reconstruction with the NRM to see bars and spiral structures around the core and the supermassive black holes in these galaxies. JWST will do phenomenally at transits as well, right? This is actually going to be one of the huge strengths of the observatory. It's an entire other hour-plus talk on all the modes for transits. But it actually is going to have the whole spectral range, 0.6 microns out to at least 12 microns. that you can do transits, you can do photometry. There's a whole lot of modes. I invite anybody who's interested in this to come talk with me later. TESS, of course, is going to be launching in Plato. We'll both be up there flying simultaneously with JWST to find objects, to find, through all sky surveys that Webb will then characterize in detail. And here's my last slide, just to end with thinking about, what does the landscape look like 10 years from now? What is AO good at? What is JWST good at? The ground will be great at doing these big surveys to find planets. Webb will not be as much of a survey machine, but will excel at characterizing them. We'll do great work in the mid-infrared, much better sensitivity, big field of view, not limited by the outer working angle problems of the AO systems. I think we'll really push into the younger, fainter, smaller planets and lower mass stars. So with that, I'll take questions and actually invite you all. This is your telescope, right? This is not, somebody else is going to do cool things with JWST. You guys have to do cool things with JWST, right? So think about it. You got 3 years. Write proposals. The question was, all the instruments are cryogenically cooled? Are there plans for a warm JWST mission after the cryogen runs out? What cryogen? There is no cryogen on the spacecraft. It's all passively cooled by that sun shield, cooling radiatively to the 3 Kelvin background of space. And so JWST will stay cold as long as it can. The only instrument that's actively cooled is MIRI. And MIRI is cooled through a recirculating cryocooler refrigerator, which also has no consumables. So the spacecraft lifetime thermally is indefinite. The maximum lifetime will probably be set just by the station-keeping fuel to keep it at L2, assuming everything else works well. So Hubble is a better telescope in terms of pure wavefront error. I don't know the numbers offhand, but it's some tens, right? So JWST is more like 100 nanometers. So in Strel ratios, you can say Hubble is 98%, 97% in visible light. Webb is going to be 95% at 2 microns, 3 microns. So it's definitely significantly worse. A nice comparison, actually, is that the wavefront error for JWST is very similar to GPI and Sphere on the ground. Our advanced AO systems are digging us down to the point where we can get Webb-like 100 nanometers RMS point spread functions through the atmosphere for small fields. This will have that image quality over arbitrarily large fields. I wish Scott Knight was still here. We had the first half of the week, Scott Knight from Ball Aerospace here, and I checked all these numbers with him. So, I think the systematic drift will be fairly small. Now, part of this is there's part of the figure form, of course, error term is vibration. So you have dynamic terms that are vibrating, of order a few nanometers. But if that's the same, the reaction wheel's in more or less the same state in your science observation, your PSF star, even though the mirrors are vibrating at a small couple of nanometers level from the reaction wheels, that ought to subtract out well in your integrated PSFs. I don't know. I would love to have better sense of all of these numbers. I think the systematic terms will be low, but then you may have these dynamic terms. The dynamic terms are hardest to predict right now. There's ongoing work to model these things and to say, again, how do we minimize this? We find there's a resonance in the correction on the cryocoolers. The resonance is tune off of that. We've actually been putting a lot of effort over the last couple months into planning, measuring the cryocooler performance on orbit, and tuning the parameters of the MIRI cryocooler to minimize the pointing jitter and things like that. We'll see.